Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Andre Weil's basic number theory, published in 1967, stands as a monumental contribution to the field, representing a synthesis of classical number theory with the modern algebraic techniques that Weil himself helped to pioneer. The work transcends a mere textbook. It offers a profound re-evaluation of fundamental principles, recasting them within the language of adeles, ideles, and class field theory. Its impact reverberates through subsequent generations of number theorists, shaping research directions and providing a rigorous foundation for advanced study. Weil's intellectual journey towards basic number theory was paved by a confluence of factors. Foremost among them was the influence of the Bourbaki group, a collective of primarily French mathematicians dedicated to providing a rigorous, axiomatic foundation for all of mathematics. Weil was a founding member of this secretive group, and their emphasis on abstraction and generality permeates his work. Prior to 1967, class field theory, a central theme in basic number theory, existed as a collection of disparate results, often proof using cumbersome analytical techniques. Mathematicians recognized the need for a unified, algebraic framework. The Artin reciprocity law, a cornerstone of class field theory, acted a truly satisfactory general proof. Weil, along with mathematicians such as Chevalier, had begun to explore adelic methods as a means of achieving such a unified framework. The desire to present a comprehensive treatment of number theory, incorporating these modern techniques, served as a primary motivation for writing basic number theory. The core of basic number theory lies in its systematic application of adelic and idelic techniques to the study of algebraic number fields. An adele is essentially an infinite vector whose components are elements from the completions of a given number field at all its places, both finite and infinite, subject to a certain convergence condition. The ideles are the multiplicative analogue of adeles, consisting of invertible adeles. Weil demonstrated how these objects could be used to encode information about the arithmetic of the underlying number field, such as its ideal class group and its unit group. He reformulated classical concepts, like divisors and valuations, within this adelic framework. For example, the ideal class group, which measures the extent to which unique factorization fails in the ring of integers of the number field, can be elegantly described in terms of adeles and ideles. Weil meticulously develops the necessary machinery of measure on these locally compact groups, which is crucial for defining integrals and analyzing a distribution of arithmetic objects. A significant portion of the book is devoted to proving the main theorems of class field theory within this adelic framework, culminating in a general proof of the Artin reciprocity. A specific and profound result showcased beautifully within basic number theory concerns the structure of the idle class group. Weil demonstrates that the quotient of the idle group by the multiplicative group of the number field itself, known as the idle class group, possesses a rich structure which reflects fundamental properties of the number field. This structure is intimately related to the Galois group of the maximal abelian extension of the number field, providing a deep connection between arithmetic and Galois theory. The proof involves a careful analysis of the topologies and measures involved, utilizing techniques from harmonic analysis and group theory. Furthermore, Weil's treatment offers an intrinsic approach, avoiding reliance on extraneous constructions and highlighting the inherent beauty of the subject. The immediate impact of basic number theory was substantial. It quickly became the standard graduate text for students seeking a rigorous introduction to algebraic number theory. Weil's approach influenced how subsequent generations of number theorists thought about the subject. Previously, many results were viewed as isolated facts. Now, they were recognized as manifestations of a deeper, underlying structure. The book's emphasis on adelic and idelic methods paved the way for further research into the arithmetic of automorphic forms and L functions, which are central to modern number theory. Mathematicians like Langlands, inspired by Weil's work, continued to develop and generalize these techniques, leading to monumental breakthroughs in the field. Basic number theory provided the essential toolkit for these developments. Basic number theory also had a profound influence on Tates' thesis, a reformulation of Heck's theory of L functions using harmonic analysis on adeles. John Tate, deeply influenced by Weil's approach, demonstrated how to obtain the analytic continuation and functional equation of Heck L functions in a remarkably elegant and conceptual manner. This work, directly inspired by Weil's methods, further solidified the central role of adelic techniques in number theory. The study of L functions is indispensable for understanding the distribution of prime numbers and the behavior of arithmetic objects in general. The book did face some initial critiques. Some mathematicians found Weil's abstract approach alienating, particularly those accustomed to more classical treatments of number theory. The level of abstraction demands a certain level of mathematical maturity. The book assumes a strong background in algebra, topology, and analysis. For some, the extensive use of adelic and idelic machinery, while elegant, obscured the underlying arithmetic intuition. However, over time, the advantages of Weil's approach became increasingly clear, and the initial resistance largely dissipated. The clarity and rigour of his exposition, coupled with the power of the adelic framework, ultimately won over the majority of the mathematical community. Weil's approach enabled simpler, more conceptual proofs of many classical results. Weil's basic number theory was directly influenced by the work of Emil Artin and Claude Chevalier. Artin's work on reciprocity laws laid the foundation for class field theory, while Chevalier's contributions to the theory of algebraic groups influenced Weil's use of adelic methods. In a sense, Weil synthesized and generalized their ideas, creating a unified framework that encompassed and extended their results. While Artin and Chevalier provided important building blocks, Weil constructed the overarching edifice. The influence of basic number theory extends far beyond the immediate circle of number theorists. Its emphasis on abstraction and its use of adelic techniques have found applications in other areas of mathematics, such as algebraic geometry and representation theory. The Weil conjectures, formulated by Weil himself, had a profound impact on the development of étale cohomology, a powerful tool in algebraic geometry. These conjectures, concerning the number of solutions to polynomial equations over finite fields, were eventually proved by Pierre Deligne, building upon the foundation laid by Weil. And, in conclusion, Andre Weil's basic number theory represents a watershed moment in the history of number theory. It provided a rigorous, unified framework for studying algebraic number fields, recasting classical results within the language of adeles, ideles, and class field theory. Its influence is undeniable, shaping research directions and inspiring generations of number theorists. The book's impact extends beyond number theory, influencing other areas of mathematics and solidifying Weil's place as one of the most important mathematicians of the 20th century. Its legacy endures as a testament to the power of abstraction and the beauty of mathematical synthesis and unification. It is a book which, although demanding in its prerequisites, rewards the diligent reader with a profound understanding of the fundamental principles governing the arithmetic of numbers. It offers a glimpse into a mathematical universe of breathtaking elegance and intricate interconnectedness.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.